Okay, so we are now recording. Okay, everyone, welcome to lecture 4 of machine learning. I want to do a quick preface. It's worth mentioning. So lecture 4 and 5 are typically some of the most challenging lectures for most students. So quick heads up. Most of what we'll cover today is either, I guess, reasonable to understand in class if you've seen some of these related ideas before, or I will highly encourage that you consider going to office hours if some of the details seem new. And we'll go in office hours in a lot more detail on a lot of these topics. So today we're going to finish up our last lecture on logistic regression, and then we'll start off on optimization, which is one of the key tools, most important tools that we use in machine learning broadly. So again, that's the agenda for today. By the next lecture, the idea of primal will make more sense. We won't actually define it today. I think it actually makes sense in the context of lecture 5. So we'll defer the definition until next lecture. Okay, so last lecture we talked about feature construction. We talked about logistic regression, at least the intro to it. For feature construction, quick check with the class. Could someone tell me why or when feature construction is important for building machine learning systems? Anyone remember? So if you remember, we went through an example for image segmentation for foreground, background, and we talked through how the feature itself may not have a lot of sufficient information to solve the classification task. However, we can augment the feature with additional information that can be useful for solving various real-world machine learning tasks. So feature construction becomes an important part of describing the problem that we're interested in solving, to capture some additional information that may not be captured by the original data as stated. So exactly, feature engineering sort of helps for classification problems, helps us better separate between classes. Okay. Next question, we talked about logistic regression. Would anyone remember how we describe logistic regression as a probabilistic model? So we talked about it as a generative or probabilistic model and used that to define what logistic regression was. Can anyone remember what this model that we constructed was? So remember, okay, so we start with a Bernoulli because we're interested, thank you. So a Bernoulli because we're interested in a prediction that was one of two possible states, +1 or -1. In order to turn our linear classification, which is going to give us some number, into a number between 0 and 1, we apply the sigmoid. We'll go through this very briefly again today. And then based on the sigmoid and the Bernoulli model, we came up with an overall model for logistic regression. So today what we're going to do is overview that in a bit of detail very quickly, and then look through how we can convert the construction in terms of probabilistic model into a construction in terms of loss functions. And then we'll contrast that with squared loss, and then we'll use that as sort of motivation for thinking about optimization in the next few minutes. Okay, so we'll go talk about logistic regression as described and then a bit about optimization. For the optimization parts of this lecture, I recommend Boyd's book, which is, I think, one of the better sources. We cover optimization in a bit more detail than you'll find in some of the machine learning books because we find that it's important for some of the material that's coming in the next few lectures. Boyd's book is free online if you look up convex optimization. And then some of the notation that we're using for the lecture. Okay, so we talked about describing or constructing probabilistic models for classification. And as you recall, the label can only take two possible choices. And so we said we'd come up with a model that works well when your output can only take two possible choices. And what we decided was that we would take our prediction from whatever model. In this case, we're dealing with linear models, right? So we have f of w and x, which we just had as w transpose phi of x, some feature function. And now we need to convert this into a prediction model. And so we said we would take this and actually push it through a sigmoid to end up with a sigmoid of f w x, right? And this sigmoid function is this S-shaped function we'll talk about in 2 seconds. And this gives us a number between 0 and 1. So this is some number 0 to 1. And we interpret this as a probability, and then we're going to use this as the basis of a probabilistic model. So in particular, if I plug in my linear model into the logistic, what I end up with is a model that looks like this for the probability of y equals 1 given x. That's 1 over 1 plus an exponential w transpose phi of x. If I actually plot out this function, which is the sigmoid function, so sigmoid of z is equal to 1 over 1 plus e to the minus z. If I plot this out, this looks like this curve. And so in this way, I can come up with a model that allows me to predict the probability of a label taking one of the states. And then we consider the opposite state of -1. And again, because there are only two possible choices, this has to be 1 minus the probability of the choice 1. And if we work it out, it works out to be a nice convenient form. It looks very similar, except the negative in the exponential has been replaced with a positive. And because of this, we decided we can take these two things together and we end up with a convenient form for a probability of the label given x. So everything comes together as a single model, which has the form 1 over 1 plus e to minus y times the prediction w transpose phi of x. So there's a quick recap of last lecture. Any questions on the basic setup so far? So from the refresher. Okay, we'll move forward. So now we want to find model parameters because again, we've come up with a model. We need to actually do the learning piece, which is finding parameters that fit this model. 1 second, please. Okay, so we want to find parameters that fit this model. So how do we choose parameters? If I give you a probabilistic model, the standard way to fit a probabilistic model is to use maximum likelihood. So find parameters that maximize the probability of the observed data, in this case, the observed data set. So we're going to apply maximum likelihood like we did for the regression case. We're going to do the exact same thing now for the logistic regression case. So one key assumption that we generally make, and we'll come back to this later when we talk about generalization and statistical analysis, but for now, and in most of the work that we're going to do, we are making an assumption that the data points or samples are IID. What does this, does anyone remember, maybe from your statistics classes, if I give you a set of points, does anyone remember what IID means? Maybe that's a good thing to define. Okay, so it's in the chat. It's independent and identically distributed. IID is independent and identically distributed. So independent means that all the data points, all the data points are independent of each other, conditioned on the data, conditioned on the input. Each data point has sort of independent distributions. Identically distributed means that they all have the same form of distribution. So data point 1, data point 2 come from the same model, if you like, which is what the identically distributed means. So we're going to apply this to our setup. If we apply this, what this means is, so independence means that we can model the joint distribution across the data by a product. So hopefully you might remember this from your statistics courses. If not, it's a good refresher, or again, worth discussing in office hours. So to refresh potentially your memory, P of Z1, Z2, Z3. If I say that these are independent, so independent, it implies that this is equal to P of Z1 times P of Z2 times P of Z3. So a quick refresher on one of the properties of independence in the distribution. So if I give you a joint distribution over data, independence means that it factors into the product of individual distributions. So we use that property that gives us this product form over the data. Second is identically distributed, which means that all of the independent models have the same modeling form. So they're all the same P of Y given X, with depending on the X and depending on the parameters. Okay, so that's our model for the data. Next, we're going to use maximum likelihood. So we want to find a setting for W that maximizes the probability of the observed data. So we do this by using the definition. So it's the maximum over the density of the data. So now it's max over W product over my data set of the probability of every single point. This probability is given by the model. So we sort of predefined model. So again, the model is here, is pre-selected, and the data comes in here, the data over which we're computing our joint distribution. Okay, so let's put all these things together. So our model is this logistic style model with a sigmoid. We are now going to apply maximum likelihood to our model across a data set. So it's maximum over W of a product, which you can rewrite as minimum over W of a sum log P. Can anyone tell me how we got from this maximum over W to a maximum over the product to a minimum over the sum? There's a key step that we use, and sort of everything goes from there. So exactly. So we apply the log. So instead of maximizing just the distribution, should put that in here. So replace this as max over W log of the product over data of P of Y I given Xi. Okay. And why is applying the log okay? So why can we replace the original optimization with the log optimization? We mentioned this briefly in the last couple of lectures ago. Okay, so the log is monotonic. All right, if we look at log of X as X increases, so log looks something like that. All right. So if my value increases, the log increases. If my value decreases, the log decreases. So it's a monotonically increasing function. So it behaves the same way. It never sort of gets smaller, and also it always increases the same rate as the input. So log is sort of well behaved that way. And so even though the value of the maximum may be different, the setting of W, so the actual W that maximizes this will be the same argmax, whether we used the original joint distribution or the log of the joint distribution. So this will end up being a really nice thing, because logs actually end up simplifying the problem a lot. In particular, first we had a product over probabilities. As we will find later in the class, particularly when we talk about clustering, products of probabilities are hard to deal with. So first nice thing is that the log turns, as we've mentioned in the chat, the log turns the products into a sum, because log of product is sum of the log. So you can just push the log through. And in addition, we replace max. So this is still a max of a log. We also then multiply through by minus. So this is also equivalent to min over W minus log of the product P of Y I given Xi. Okay, and once you have that, the rest should follow through. So the log product becomes a sum, and then that's how we end up with this equation on the top right. Okay, so those steps. Combining together, we end up with a nice form. So if I apply the log to my original model, what I see is that log 1 is always fixed. It's a constant, so that's 0. Log of a ratio is log of the first term. So log of A over B, as you might remember, is log A minus log B. All right. So that allows us to separate out the numerator and the denominator, so that's convenient. And we end up with log of 1 plus e to the minus y times w transpose x. So this becomes the thing that we need to optimize. Okay, so it turns out that this resulting loss function we can write in the standard sort of loss way that we like to write optimization problems or to write learning problems. And to do this, we'll compare it to what happens in least squares. So if I look at least squares for classification, if you recall, the loss function that we ended up optimizing is the prediction, which is w transpose phi of x. So prediction over here, multiplied by y, and then you do 1 minus this y times the prediction, squared the whole thing, and then sum over the data sets. So this was our loss function for least squares for classification. If I write down the least squares for regression, you can hopefully easily identify the same components. So once again, I have our prediction multiplied by the label. And now instead of a squared term, we have this log and exponential as our definition of the loss function. So in particular, our loss function takes the form log 1 plus e to the z. So that's the loss that we're getting from here. Whereas here we had the loss function equals to half 1 minus z squared. This should be 2. Okay. So I apologize. There should be 2 and that should be z. Okay, that's a bit clearer. Anyways, so they both have a loss form. They both use the prediction w transpose phi of x, which is the linear prediction. So linear prediction, loss, average over data. So they both take that same form. And in general, for supervised machine learning problems, we're going to take this view of empirical risk minimization, where all of the problems that we're solving will take the form of, sorry, it's possible that there's a minus missing. I'll double check that later. So all of the problems that we're interested in solving, I think that's right, actually. All the problems we're interested in solving will be sum of some loss function over the data. So loss between our prediction and our label. So label, prediction, some notion of loss between them. We've looked at least squares, we looked at logistic, and then averaged over the data. So this is the general notion of empirical risk minimization. Empirical because we're using average over data. Risk because we're minimizing a loss, and average loss is called a risk. And minimization because in all these settings, we're minimizing to find a good parameter setting. So this is the notion of the way that we're going to be using for picking different kinds of, for solving different kinds of machine learning problems. We'll often try to rewrite them as some kind of empirical risk minimization problem. So there's a question of which loss is better to use. That can be tricky. Today, we're mostly making the case for logistic loss as an improvement over squared loss, least squares for classification problems. We'll spend some time later again thinking about how to empirically evaluate sort of which loss might be a better fit to a particular problem. We won't go into a ton of detail. There's more advanced classes that talk about some discussion on how to pick loss functions. I would say it's still a tricky problem in practice, but there are some good rules of thumb that we like to follow for picking loss functions. Okay, so oh yeah, let's see, I messed this up a bit. Said I was going to change this. I should. So that should be minus C, as was pointed out in the talk. So we can plot out these curves and see what's going on, which hopefully gives us a motivation. So what I'm showing here is the sort of y times prediction on the x-axis, and then the loss function on the y-axis. And what you can see is that squared loss does what we described last time. So if your prediction is exactly 1, you get the lowest loss. Otherwise, you pay a penalty, both if you make a mistake, but also if you're correct. So both if you're correct or if you're wrong, you pay a penalty. Logistic loss, if you plot out what it does, when I'm incorrect, I pay a penalty for being incorrect. However, if I'm on the right-hand side, so if I'm correct, I pay a much smaller penalty. This will come back later on. So the penalty for being correct is not 0. If I look in here, there's still a gap. So sort of penalty for being correct. There's sort of this gap over here, but it's much better behaved. So when I make the right decision, I get a low loss. When I make a wrong decision, I get a high loss. And remember, what we want is to minimize the loss over the data. So find me a parameter setting. So find me a W that makes the average loss of my data as small as possible. That's the target task. That's what we're hoping to solve. And logistic regression behaves much more reasonably than squared loss in terms of how it behaves for making good or bad classification decisions. Okay, any questions so far? Okay, we'll move forward. So let's talk about how to optimize, to actually pick the W. Very quickly, there's a question on, can I use squared loss for logistic regression? So this is actually quite an important question, and I don't know that I emphasized this sufficiently before. So both logistic loss and squared loss are what are known as surrogates. The actual task that I'm interested in this problem is to maximize the number of good predictions that I make. So I'm interested in accuracy. I'm interested in minimizing the number of mistakes in my prediction, right? So this is the 0-1 loss. This, the 0-1 loss, the black curve. That's the thing I actually care about. That thing, as we've discussed a few times, is hard to optimize. So I don't know how to optimize this 0-1 loss on real problems. This is not an abstract thing. This is actually very precise. It is computationally hard to optimize 0-1 loss on real problems. So instead, I use what are known as surrogates, so other losses, and I optimize other losses that are easier to optimize, and I optimize those losses instead. So y times f should be between -1 to 1. So remember, the prediction can take any value in the reals, all right? So f is w transpose phi of x. This is in R. So y is +1 or -1. The prediction is any number, any real valued number. So y times the prediction is any real valued number. If w transpose phi of x is the same sign as y, it will be on the right-hand side, greater than 0. If w transpose phi of x is a different sign than y, you'll be on the left-hand side, less than 0. Does that answer the last question? Yeah, so there's no sigmoid here. The sigmoid was when we defined the probabilistic model. The sigmoid has gone away because if you expand out to the loss function. So this is the actual loss function, right? There's no sigmoid in the setup, if that was the reason for the question. So does the log loss look different? So the question is about whether the log loss looks different, whether we use Bernoulli or not. These are tied together. If I choose a Bernoulli, what I get out is a log loss. So logistic loss is what you get out if I use a Bernoulli model. So remember, this is how we defined it. We started with a Bernoulli model, we got out a log loss. If I use a different model, I'll get a different loss function. So these two are tied together. They're the same. Well, they're tied to, the two quantities are tied to each other. By choosing a Bernoulli model and sigmoid, I get out the log loss. And so that becomes the loss function in terms of the optimization problem that I'm looking to solve. Can you use log loss for binary classification? That's exactly what we're doing. So I'm going to use, I'm going to optimize the log loss, and then I'm going to use sine of W transpose X. So the prediction is sine of f of X, or sine of W transpose phi of X for our linear model so far. Can we use, what is the 0, 1 loss? So 0, 1 loss is equal to an indicator function of whether yi is equal to the sine of f x I w. So we covered this in the last, I think 2 lectures ago, and briefly in the last lecture. So that's the indicator, that's the 0, 1 loss. It's checking, did I get the prediction exactly right or not? Can we use the piecewise? You can come up with, there's a whole part of machine learning that comes up with new loss functions. It's an art, can be an art. Almost always we try to pick loss functions that are tied to some real task. Again, that's somewhat beyond the scope of this class, but I work on this as part of my research. I'm happy to talk to any one of you if you're interested about some details of picking and designing loss functions. But here, we're motivating probably the most popular loss function for classification, which is logistic loss. And the way that we motivated it, if you like, is 2 ways. One, we said, if I choose a probabilistic model, which is Bernoulli plus sigmoid, what I get out is logistic loss. Alternatively, you can motivate it based on the behavior of this curve. It's a loss function that penalizes you badly for making an error, penalizes you less for making a good decision. So it behaves much better than quadratic or squared loss for classification problems. Can we use the sigmoid as a loss function? You can, so there's an interesting question. Can I use, so here's another loss function choice. This slide has become exceedingly busy, but hopefully in video it makes sense. So here's an interesting choice. I could do the following: y times sigmoid W transpose phi of X. So can I do this instead? Yes, you can. It turns out to not work all that well in practice. There's some good reasons for this. If you remember this question by the end of lecture, ask me again, and maybe we can go through why this particular loss tends to be not a good one from the point of view of fitting learning problems. But it's a very reasonable choice. It says, you know, put a sigmoid combined with squared loss. Can we do something like that? That's what I interpreted as that last question. It's possible that you meant something else. Is that what you meant, Seth? Okay. Okay, so now we're going to talk about optimizing for logistic regression. So remember when we solved the ordinary least squares problem, all we did was, well, let's work out the gradients, set the gradient to 0. This is sort of calculus 101 that you might remember. And based on setting this gradient to 0, we found a closed form solution for the least squares. Now the question is, can we still do this for logistic regression? Any guesses? So maybe a quick poll. Can we solve least squares the same way? Sorry, logistic regression the same way. So set the gradient to 0, solve for W. Okay, so almost everyone that has responded so far thinks no. You can write down the gradient. I'm not going to derive it, but it's not that hard to derive. It's a nested function. We're interested in the gradient with respect to W. You can work out the gradient here. The gradient looks a bit complex, but it's actually, we'll come back to this. It's very reasonable. So I can work out a gradient. I can set this to 0. This gradient is a complicated nonlinear function. It turns out that there's not an analytical solution for W. So I can't come up with a simple plug-in rule where if I give you a data set, here's a simple plug-in rule that gives me the solution for W. So simply plugging in and setting gradients to 0 doesn't work. So we're going to try a different strategy for trying to find a good setting for W. So instead, we're going to use what is known as gradient descent. And we'll spend a lot of time in this class talking about gradient descent. Here's our first introduction to the idea of gradient descent. So one intuition for gradient descent is walking down a mountain. If you like, you can think of the behavior of the loss function as a function of W as a mountain where some values of, so this is loss and this is W. Actually, this is not a good, sorry, I wrote the wrong curve. So we're trying to minimize a loss function, and the curve over data will look something like that. So it's a U-shaped curve. And we're starting at some point. And we want to get to this value, which is the minimum of the loss. So we want to find min over W of the loss of W and other stuff. And so one good way to try to solve this problem is to try to start from some initial guess for W. So this is some guess. And then try to improve this guess over time. And what gradient descent tries to do is exactly solve this problem. So it starts with initial guess for what the solution is, and then we slowly try to walk down the mountain till we get to the best value for W. So this is W that has the lowest loss on this data set. So in 2 dimensions, which is actually a much better illustration, it looks something like this. Same exact intuition. I start from an initial guess for W, which is away from the lowest value of W, and I slowly try to walk down the mountain. You haven't seen this before. This is a level set curve. You can call it, if you look at a map top down, and you see it's a topological visualization of a map. So we're trying to show like 3D views and 2D. One of the ways that we do this is that we draw plane curves. So these are curves. If I slice the 3D, if I slice my 3D mountain, so I slice this mountain at different planes, I get a sequence of, in this case, I get a sequence of sort of circles or spheres. But more generally, I get a sort of a plane curve that I can use to visualize what's going on in 3D. Thank you. I forgot the term. Contour curves is also what they're called. Thanks. So I start from a point. So you can look up contour curves if you want to understand a bit about how we're visualizing what's going on. But this is a 2D version of what I just showed in 1 dimension, where now W is a 2-dimensional quantity. So there's a 1W, 1W2, so 2 dimensions. And again, I start from a point, and what I'm looking to do is to find the minimum. And so I start from a point, and I need a sequence of steps to sort of iteratively improve my choice, or my choice of W. So find better and better W's. So how do we do this? Well, one good way to walk down a curve is to use a gradient. That's the definition of the gradient, is the direction of descent locally around a point, if you remember. So what we're going to do is we're going to start with an initial guess of W. We're going to look for a direction of descent, so a direction to improve W. There's a direction that makes our loss better. And we're sort of sequentially going to follow this direction until we get to the best choice of W. So this is what gradient descent does. Okay, so the algorithm is super simple. We start at some initial time with some WT. We pick a step size, so how far we're going to step in a gradient direction. We compute the gradient at the current point. we take a step in that gradient. So WT minus some step size times the gradient. So in our picture, we start with an initial point. We pick the gradient. So this is a vector in the direction of best descent, locally around WT. And then we take a step of size alpha in that direction. And so we do this, so this is minus gradients, sorry. And so we do this over and over again till we get to the minimum, and we just keep increasing our counter. So this is gradient descent. This is the bread and butter of machine learning. We'll use this a bunch of times today and then pretty much all through the class. And you'll come to both love and hate it as sort of the sort of hammer we use for solving most machine learning problems. So how do we choose the step size? We'll give a first version today, but more conceptual and analytical. In practice, it's done by tuning. We'll talk a bit about this when we start building some real models. Do we choose a constant step size, or do we solve another optimization to choose it? It depends. In practice, most of the time we use a step size update schedule. So you either fix a step size and just use it all the way through, or there's a simple update schedule where the most common update rule is that I pick my step size as maybe some quantity divided by t plus 1, something like this. So this is by far the most common update rule, but you can think of other kinds of update rules. There's a whole literature that we don't do justice to that covers what the properties of different step size update rules are for different kinds of optimization problems. For convex problems, there's a lot known about how to pick good step sizes. For other kinds of problems, as when we get to neural networks in the future, it gets a little tricky to pick good step sizes. There are some good heuristics, which are built into many of the packages that we'll end up using. But step sizes are actually an important part of building, of optimizing machine learning models in practice. So why is it minus? So we're trying to go into negative gradient direction because we're trying to, I guess, locally decrease. I'll push that offline, actually, maybe have longer conversation about that. Okay, so we're covering just a very basic gradient descent. There are many, many other extensions. So we won't cover them. I'll mention at the end of class some other methods that you could use. And it's known that if I pick a better method, then I can find a solution faster than basic gradient descent. Okay. Some answers already in the chat, so I don't need to answer. So yeah, so gradient is increase and we want to get the decrease. Okay, so let's talk a bit about how this works for some real problems. So again, we were motivating using logistic loss because we had data that say looked like this, where spread loss behaved badly. So if I plot out the loss function, this is a simple problem where W is two-dimensional. If I plot out the loss function for this problem, here's an example of what it looks like. Here's also an example of a contour plot. So this is the actual 2D curve on the top, and sort of here's the contour plot at the bottom. And so you can imagine if I start at some point here, which is equivalent to here, what I want to do is sort of get to the minimum, which is equivalent to sort of taking steps. I guess the minimum is actually over here. So that's the task that we want to solve. And if I apply gradient descent to this problem, you can see that it does exactly this. So it finds me a descent direction that ends up minimizing this loss function. And if I look at the probability model that I end up fitting, the P of y given x behaves as you'd expect. So the probability of class -1 is on this side. So this will classify as -1. And this will classify as +1. Right. So unlike the squared loss case, where this is a really good question that came up. How do we know that this is the global minimum? We'll talk about this today. So unlike the squared loss case where we found that the squared loss solution found a threshold that would behave a bit weirdly, for the logistic regression case, this does what we expect. So this actually finds us the solution that matches our expectation. And it turns out that in practice is also, it tends to outperform squared loss as a better sort of loss function to use for optimization for classification problems. So almost always, if you try to design a classifier, in general, we use logistic loss is the first thing you should probably like pick up as your first loss function choice, because it's the most sort of well understood, and it's considered a safe initial choice for many other reasons, some of which we don't cover in this class, some of which we'll cover in a couple of minutes as a good choice for a loss function. But here's an example where it does what we hope that it does. Okay. So the red line, I'm trying to answer some questions. So this is our estimate of Py equals 1 given x. It's this guy. That's the red curve here. And these red lines are the gradients. So this is Wt minus alpha gt. So this is the direction over steps. This is sort of the iterates as we're solving gradient descent along the contour plot. Other questions? Okay, yeah, everything else seems fine. There's no other questions. Any other questions so far? Okay, so so the question is, we decided to use Bernoulli so that we could introduce a log loss. Short answer is yes. So Bernoulli is a natural model. It's probably the natural model if you have two choices. You can, of course, make things much more sophisticated, but it's the natural model for modeling a discrete distribution that has two options. The more of the modeling choice was the use of sigmoid and use of a linear function. I think those are the things that were there may be more modeling choices. You, of course, can make the rest of this much more sophisticated. I think what's useful to keep in mind, or to as a takeaway, is if I start with a Bernoulli, use a sigmoid and a linear model, I end up with linear logistic regression. But linear logistic regression can also be justified on its own, just based on its loss properties. We think that, or I think that justifying it from a probabilistic model point of view is maybe the most natural way to motivate it. But you can always just say, I want to use log 1 plus e to the minus z as my loss function because it behaves nicely. Again, I'll defer it offline to additional discussion of how one might design loss functions for different problems. So you can always design different kinds of loss functions. So we'll stop that. I think for that discussion, that's where we'll stop for now. Multi-class is a future class. We'll talk about that multi-class in a future lecture. Can we convert? So yes, this is a good question. So what happens if alpha, yes, okay. So I guess it's already answered, but maybe we can have a bit of discussion about this. So I glossed over this, but it's actually true. It's worth emphasizing that, okay. So it's worth emphasizing that choosing the right alpha can make a big difference. If alpha is too big, then you can essentially go pretty wild and it can take an extremely long time to converge. If alpha is too small, then the optimization can be really slow and it'll just take also a really long time to converge. So picking a good alpha is actually a super important step. Again, in practice, there are rules of thumb, and in special cases for certain classes of loss functions, like the loss functions we'll talk about today, we'll give a bit of discussion on how some good schedules for picking step sizes. X and Y axis. So on this plot, the Y axis is the data, which is this guy and that guy, and then also the probability. So we just put them on the same plot because it's convenient. So the probability is the red curve, and the data is the blue circle and the black x's. And the x-axis here is one of the dimensions of x. So x is the dimension. Again, I'll just draw it again. So here is phi of x 1, because in this toy example, that's the only place that there's signal. And this example, the y-axis is y, and also p of y given x. On this curve, we've gone to the two-dimensional setting to visualize the point. So this is W2, second dimension of W. This is W1, the first dimension of W. And this is the loss function. So this is loss as a function of W1 and W2. Hopefully that answers your question. Okay. Okay, cool. So let's move on. I'm pretty sure we won't finish this lecture either. Again, though, I appreciate that there are lots of questions. So I think hopefully this is helping in understanding some of this material. We'll likely end up finishing some of this next time. But anyways, let's keep going and walk through stuff. Okay, so far we have seen least squares regression and classification, where we use squared loss. We've also seen logistic regression, where we use logistic loss. And in the squared loss case, we said we could solve it by an analytical optimum. So we just found a plug-in answer, and we did this by computing the gradient, setting it to 0, and then plugging in to get the right, the optimal W. In the logistic regression case, this plug-in method didn't work, but we found an easy alternative. So we said we can use gradient descent, compute the gradient at every point, and then incrementally follow the gradient so you get to the local, to the optimal. If you can please turn off your microphone. Thank you. Okay, so can you solve least squares using gradient descent? Anyone guess? Okay, yep. So again, you can always apply gradient descent to any loss function. Today we'll talk a bit about when it works, when it's guaranteed to work, and when we're not sure. It may or may not work. So today we'll talk mostly about sort of cases where we know gradient descent definitely works. And least squares will turn out to be one of those cases. And in practice, actually for really big problems, gradient descent is much more commonly used than a plugin. So it's actually quite rare for sort of practical problems to solve even least squares regression by using the analytical solution. Okay, so again, in all the problems that we've described so far, so we're interested in empirical risk minimization. We've set this up as minimizing the average loss over data. The question is, how do we find a good set of weights? So we've said that we're going to use gradient descent as a sort of general strategy for all these. Now we're going to work through why it should work and when it can go wrong. So to actually set this up a bit, let's visualize this sort of 1D. So we started with this simple example, and we said that we're going to use gradient descent to walk down this curve to find the minimum. So hopefully you mostly agree that in this situation, gradient descent will be fine, because I'll sort of go through and eventually end up in the optimum. So this is nice because this is, in particular, what is the gradient at this point? Okay, so gradient is 0, right? Because it's a flat region. So the definition of gradient, again, will easily show that as we get closer to an optimum, the gradient gets closer to 0. And in particular, we know when to stop because the gradient is 0, right? However, suppose this curve was something like this. And suppose this point is lower, right? So this point has a lower loss. Then will gradient descent work in this case? So in general, no. So it could fail. So if we happen to be in the right basin and started from a point close to the right optimum, then we know it will work. But if we say, so in this setting, suppose we started here, then it'll follow the right gradient. If we start here, then the gradient will always push you in this direction. So it will never find this better solution. And the reason is that gradient descent is a local optimizer. So it only knows information locally around the points that you've given it. And it can only use that information to make progress. So in order to sort of find global solutions, we need to know global information. Now, what we're going to talk about today are classes of problems where local information actually gives us global information. So these are classes of problems that have special structure such that local structure implies global structure. In particular, gradient descent will provably work for those kinds of problems. So as we've discussed, many of these have names. So the global optimum is typically considered the ideal solution, what we're targeting. Local optima or local minimum are points that are locally the smallest value in their neighborhood, but may not be the smallest value across the whole function. And a saddle point is a flat region that's not necessarily a global or local minimum, but it's at a locally flat region. So if you like, this is just, it's a point. Remember, all of these special points are points that have gradient 0. So at this point, gradient is 0. At this point, G is 0. And at this point also, G is 0. So if we're applying, if we're depending only on gradient in order to find solutions, we can't tell apart whether we're in a global optimum or a local optimum or in a saddle point. Okay. I don't understand the last comment. Okay. Okay, so let's talk about special sets of functions where this works. These are known as convex functions, and we'll have a whole discussion about convexity, where I expect that we'll start today and then likely finish in the next lecture. So let's start with a bit of definition. So we say that a set is convex if it contains all of its line segments. So if I give you a set like this, is this a convex set or not? Be quick. Chat poll, no. And it's not because I can draw a line segment that crosses across the sets. A set like this would be a convex set because any line segment I can draw will always be within the set. So it's a sort of simple rule of thumb way. We'll make this more formal in a couple of minutes, but a simple rule of thumb way to define convex sets is a set that contains all of its line segments within it. So again, from examples, if I give you any 2 points in the set, then the line segment between and those 2 points are within the set. So more formally, if I say a set C is convex, then if I give you 2 points, any 2 points within that set, then it implies that the line segment, so this is notation for the line segment, that the line segment between X and Y is wholly within the set. So it's completely within the set. So how do we describe the line segment? So if I give you 2 points, then you can always define the line segment by a convex combination of those 2 points, where the convex combination is some alpha between 0 and 1, right? So if alpha is equal to 0, then alpha X plus, this is somewhat tedious. I probably shouldn't have done this. I just make my life easier and erase. If alpha is 0, then I'm at point Y. If alpha equals 1, I'll be at point X. And then for any other value of alpha, I can interpolate between X and Y. So that's a simple way to describe a line segment between 2 points X and Y. So the intuition that we just described, a convex set being a set that contains all its line segments, I can write more formally as given any 2 points within the set, the line, which is described by this alpha convex combination between X and Y, is always within the set. Okay, so that's the definition of convex sets, if you haven't seen it before. Questions so far? Okay. So now we're going to describe convex functions, which will be the set of functions that we're going to end up spending a lot of time talking about in terms of optimization and learning. So first we need to describe an epigraph of a function. So an epigraph of a function is the set of, well, the intuition for an epigraph of a function is if I take any function and bucket fill, so I take all the points above that function, that's its epigraph. So suppose this is the range of my function, and I take all of the points above this function. This is f of x. This is the epigraph of f. So it's a functional. It takes in functions, returns sets. So this is all of the set of points that are lines, or sorry, all of the set of points that are above the function is the epigraph. So it's the set, it's the combination of the point and then sort of either f of x or any of the points that are above it. Okay, so intuitively, this just looks like bucket filling a function from above. So we say that a function is convex if its epigraph is a convex set. So intuition again about epigraphs, if I take a set like the U-curve that I drew before, if I bucket fill, so let's actually do this explicitly. If I bucket fill, I get a set that looks like this. And now we can apply the test that we discussed before, which is, can I put all line segments within the set? So if I draw any line, the line always remains. So this line or that line always remains inside the set, which means that this set is a convex set, which means that this function is a convex function. However, if I take a line like this one on the right, so I won't redraw it. So again, I can draw the epigraph, which is all the points above it. And now if I try to check whether this set is a convex set or not, I can easily find 2 points that are within the set, but the line between them is not within the set. And so this is not convex. And this is convex. Okay, so this is an example of convex and non-convex functions. Okay, so we've just described this somewhat intuitively. So there was a question about concave functions. That statement is not true. So a function is not concave just because its epigraph is not convex. So in particular, this function, its epigraph is not convex, but this is not a concave function. So the easiest way to describe concave functions is that if a function is concave, so f is concave if minus f is convex. This is my suggested, and I think the most convenient definition, at least for purposes of this class. So think of concave functions as negative of convex functions. So in particular, a concave function, the generic concave function looks like a cap, which is the opposite of the U-curve, which is for the generic convex function. So so the statement is not true. So it's a bit more complex than that. You can have functions that are neither convex nor concave, like this one, and also some not concave. Thank you for the question. That's a good question. Hopefully educational for the rest of the class as well. Okay, so now we're going to try to describe this notion of epigraph as a definition of convexity for functions. But instead of trying to draw pictures, we're going to convert this into math because that's what we like to do. So now we're going to try and describe convex functions by a set of properties. So now we say that a function f is convex if this property holds. Now, again, I can convert this property into intuition. The intuition is exactly the same as before. If I draw my function f, this is the weighted average of 2 points of the function. So to make sure axes are concrete. So this is x, this is f of x, right? And I take 2 points along the curve. Right. And this is saying draw the line between the functions. And it's comparing it to drawing to the function evaluated at the average of the 2 points. So the average of the 2 points, so suppose this is point 1, point 2, the average of the 2 points is here, and the function evaluated at the average of 2 points is here. And we say that a function is convex if the function evaluated at the average of 2 points is always less than the average of the 2 function evaluations. So again, I evaluate the function at 2 points, and then I evaluate the function at the average of the 2 points. And the function is convex is for every pair of points, this is always less, this is always below the average of the function at the 2 points. So that's what this whole description is saying. This part here is the average of the function. This part here is the function of the average. And a convex function always satisfies that the function of the average is less than the average of the function. So that's the property that we are looking to check. So in contrast, for instance, again, we'll draw our favorite non-convex function. So I pick 2 points, a point here, a point there. Again, be precise about axes. And I'm going to draw a function. I'm going to draw the average of the 2 function points. And I'm also going to draw the function at the average. And here we can see that the function at the average is bigger than the average of the 2 function points. So this tells us that this function is non-convex, whereas this first function is convex. It is, that's interesting. So the question is this related to triangle inequality? Very vaguely, let me see. Sort of, I've never thought about it that way. That's interesting. I want to be careful, so I'll defer, but it sort of acts like a triangle inequality, but I didn't want to suggest that as intuition. So let me think about that a little bit more. If you could ask on Piazza or something, I can think about that a little bit more. But it sort of acts like a triangle inequality very, very vaguely. Yeah, good question. Okay, so now we've defined convex functions. So we started, just to recap, we started with convex sets. We said that these are sets that contain all the line segments. Then we defined the epigraph of a function, which is all sort of water filling above a function. So this is all the points above a function. And we said that a function is convex if its epigraph is a convex set. And then we converted this intuition into a simple mathematical definition, which ends up just checking whether the function at the average is less than the average of the function. And if that is true, for every set of points, every pair, we say that this function is convex. And if that is not true, then we say that this function is not convex. Let me answer some questions. So does alpha take other decimal? So the alpha can be any value between 0 and 1. This is true for all alpha. This is a good question. Actually, this is here. This is true for all alpha 0 and 1, including 0 and 1. So that has to be true for all possible values of alpha and all possible values of x and y that are within the range of the function. It's also closely related to Jensen's inequality. We'll talk about this a little bit more later, much later. But if you know Jensen's inequality already, it's actually, you can derive this easily from Jensen's inequality. It's the same quantity. The next question says, why are you only looking at one point on the function for the left-hand side, but the whole line? So this is not a whole line. This is 1 point. I apologize. So this average of the 2 functions is this point. So this is average function, and this is function of average. Okay, so it's 1 point to 1 point comparison. So it's not a function to function. I think I was unclear on that. Again, this is average over 2 points. So this is 1 function point, and this is also 1 point. And we're comparing these two. And which one is bigger tells us whether, and again, this has to be true for every pair of points and for every value of alpha. And this tells us whether the function is convex or not. Okay, so convex functions, intuitively, these are functions that have no bumps. One really nice property that we may or may not get to today, if we don't get it today, we'll get to it next lecture, is that convex functions are functions with no bumps, and gradient descent works when for convex functions. So we'll cover some of the theory. There's a lot more. The entire optimization class is on convex optimization. We'll cover a little bit of the analysis for very simple cases, but the rough statement is that gradient descent works for convex functions. And where we're hoping to get to is that both of the problems we've come up with so far, logistic loss and squared loss, work out to be convex problems. And so provably gradient descent will give us the right answer. The next question is, what if the convex function doesn't have a minimum? That's fine. I need a bit more context for that question, actually. So what is the context of the question of not having a minimum? So we haven't talked about optimization yet. We'll get to that later. Yeah, if you add more context, I can answer that previous question. The question of average. So this is a weighted average. That's a good question. So this is a weighted average. I don't know where else. Let me just write it here. Weighted average. As I change alpha, I go between, so this is alpha equals 1, alpha equals 0. This is alpha equals 0.5. This has to be true for all alphas. So I picked a single alpha, but this has to be true for any alpha I pick. It's a great question, actually. So for any alpha I pick, I need this relationship to hold, that the average, the weighted average of the function is always bigger than the function of the weighted average. Sure. So a function can be both convex and concave. A function, we've said nothing about minimums here. We're not using any property of minimums yet. We'll talk about that later. All we're asking is this property. So function of the weighted average is less than the weighted average of the function. That's all we're doing. Let's hold off on minimums till we need it. We haven't used that at all. So to be precise and actually clarify, so none of what we've discussed so far uses minimums, right? This is just definition of convex functions. There's no minimum anywhere. We'll talk about that later. So we talked about, okay, so I guess minimum is regards to gradient descent. We'll talk about, so the thing that we're interested in solving is to find, so we're going to apply gradient descent in cases where the minimum is at infinity, for instance, so something like exponential. We'll talk a bit about some of the properties that show up. Actually, I don't think it's in the slides. So ask this question again when we talk about the actual optimization. And we'll talk about what happens in practice. It actually works out fine, but that's actually a good question. So I guess looking ahead a bit, we don't need to do anything special in terms of what we're doing in gradient descent. In practice, we know that things like exponential have that property and end up having a certain effect on what the optimization, the gradient descent optimization does. However, in almost every setting, we use regularization, and it turns out that regularization fixes this no minimum issue. So the actual problem that we solve in practice is a regularized logistic regression, where we use like the L2 regularization, like we talked about for ridge regression, and that always has a minimum. So that ends up being well behaved. It's a good question. Thank you. Okay, so we have 5 minutes. Let's see how far we get. Again, I guess I predicted correctly that I wouldn't finish this, but again, I hope that you're asking questions that are helping to understand what we're working through. And
really quick question on this slide.
I prefer non-voice till afterwards, after we're done recording. So if you want to ask it by voice, hold 5 minutes or so, and then we'll turn, and then you can ask voice questions. But now I prefer text, if you don't mind. Okay. Do you want to try asking by text? I'll keep an eye on that. Or like I said, once we are done with lecture, I'll hang around for a few minutes and I can answer questions by voice once we're done recording. Okay, so there are lots of convex functions out there, exponential, negative log. So we can draw most of these. It's easy to check that they're convex using all the rules that we've talked about so far. Norms are convex functions. Negative entropy is a convex function. Log sum exponential. Many of these will show up in the future for many problems that we're interested in. So these are good examples of convex functions. Okay. So in addition to convex functions, we'll look at losses. So quadratic loss, log loss, the two that we've talked about so far. So it's clear that quadratic loss is a convex loss. Again, easy to show using the properties we've covered so far. In fact, it's been the main example that we've used. It's also easy to show that the log loss is convex. Either show it directly with the epigraph or use the rule that we just talked about. So show that for all pairs of points, the function weighted average is always greater than the average of the, so the function of the average of the function is always greater than the function of the average, weighted average. Okay, so we'll talk about how to prove these properties. And we'll also try to build up to convexity of the loss function we're actually optimizing, which is this average loss over data. So the first part is showing the convexity of a single example, so loss of a single example. This is L of Y W transpose X. And then we'll build up to loss average over an entire data set and show that this remains a convex function. And because of this, gradient descent will behave well. Okay, so in the last couple of minutes, I'll just go over some special kinds of convexity. And then we'll use them in the next lecture after a quick overview. So convexity, as we talked about, it's simple to check if a function is convex. So we talked about using this line property. So that's the most standard way this always works. We can also use derivatives. So if a function is differentiable, then we can check convexity based on derivatives. Roughly, convexity implies that the sort of slopes are increasing with respect to the direction of the function around its minimum. So that's an easy way to check if a function is differentiable. Importantly, convexity and differentiability are two different properties. So a function can be differentiable and not convex, and a function can be convex and not differentiable. So that's important. They're two distinct properties, but if a function is differentiable, it makes it a bit easier to check convexity. So it's a sort of easier property to check. If a function is twice differentiable, so if it can compute the second derivative, then we can check if the second derivative is positive semi-definite. So the second derivative, also known as the Hessian matrix, is positive semi-definite, then the function is convex. And this is positive semi-definite at every point. So if you like, the intuition roughly is that the function can be lower bounded by a quadratic at every point. This is one way to think about what's going on. Okay. We can also, so we can check some examples. So squared loss is convex. One easy way to show it is to take derivatives. So the first derivative is z minus 1, second derivative is 1. So if you use a second derivative test, second derivative is positive, so it's going to be a convex function. The first derivative we can also apply with the first derivative test that we talked about, or you can use the function value itself. And so you can show in all these ways that the function is convex. Logistic loss is convex. Again, you can show it with the same set of properties. That's sort of a general set of rules for checking that functions are convex. We are done on time. Next time we'll talk about strict and strong convexity. Now we use strict and strong convexity to build some analysis of how gradient descent behaves for strictly and strongly convex losses, and then tie that into what we do for some of the losses we already considered and some losses we can consider in the future. So with that, I'm going to stop recording.